This is a brief breakdown on how I made this mesh unfolding effect using Blender 4.1's geometry nodes. This could be done in Blender 4.0, but 4.1 has some good rotation nodes that I wanted to take advantage of. So, I'll give you the brief overview of all the steps and then go through each node group here to show you how it is done. So to start off, over here, we store the parent face. So with this mesh, each face essentially has a parent. This face looks at this one looks at this face, and so on. And then we get the parent face corners. So this would be the face corners that are on the edge line that joins with the parent face. Now, since this uses an edge split node later on, it has to be the face corners and not the edge index. After that, we store the transforms of the faces, just so that we can make the transforms local afterwards. We split the faces because that's necessary so that the mesh doesn't get all mangled together when we do the new transforms on the vertices. Then we get the local transforms so that we can get the one face's local rotation to the next face, its location, rotation, scale, and so on. And we also store the local vertex position to the face so that we can then reconstruct the vertices later. Next, what we do is store a gradient to control when the effect happens, and then we restack the face transforms, and then we reapply the new vertex transforms by the face. So, if you didn't understand that, that's perfectly fine. This is a complex effect. So let me go over the node groups. So right here, we get the parent face. So with this, we can take advantage of the shortest edge paths node. Now with the dual mesh node, we can convert face to vertices. And with that, we can then get the shortest edge paths and the next vertex index. That is our parent index. So with that, we transfer that back to the regular mesh from the point domain to the face domain. Because of the dual mesh, that's what it does. It converts face to point, so we convert that back. And then we get the total cost, and we set this to 1 so that as the total cost gets stacked up as it goes along, it gets transferred as the loop ID for when we restack all of these faces. And once we have that, we get the parent face corners. Now, this setup was very annoying to figure out, but essentially, it looks all the face corners, look at all the face corners on other faces. That's what this part does. Then it sees which ones are on the parent face. So if that's true, we go and use that vertex corner, put it into the weights of the corners of face node, and then that'll give us our parent face corner, which in this case, for this face, would be right here or right here. It's a little funky with how the order goes. But then, to get the second face corner, we just go and offset it by 1. That's the easy part. I was very happy when I found that out. So after that, we then store the transforms. So in this case, we get the 2 face corners that we just got, and then we subtract the 2 to feed it into an align Euler to vector node to get the x-axis first, which is very important, and this is set to auto, so that's the primary axis. And then we set the normal as the z-axis on the x pivot. So we store that as the face rotation on the face domain, and then we store the face position where the average of these 2 face corners are. That's so that the face corner, its position is read as right here instead of the middle of the face. So this one's face position is right here, this one is right here, because that will control the rotation axis later. And then we can store the face scale. I did it as just a float. It's not too important. A float scale should be fine for now. And then after that, we split the faces so that we can then store the local transforms. Now this is fairly, okay, not exactly straightforward, but the logic is sound. We first go and take the face rotation, and then we see what that is on the face parent, which we evaluate at the face index right there. We invert the rotation, and then we feed it into a rotate Euler node. Now it's important that we have this on Euler and local, so that we can rotate these along the correct axes later on. And then we do the face local position. Now this uses a custom node group that I set up. Now this one isn't too complex. We basically have a regular transform option right here, and then undoing a transform. So doing what the transform geometry node would do, but in reverse order. We take away the position, then the rotation, and then the scale. So that's how it works. Once you get the setup, you don't really have to look inside of it again, but it's good to know. So now that we have this, we evaluate the face position, we put that into the top, we get the face parent position and the face parent rotation here and here, we plug those into there, undo the transform, and that is our face local position. For the face local scale, it's just 1. The default is 1, so you don't really need to store it. These two are on the face domain. So next is the vertex local transform. As we can see here, we're doing a similar thing to right here. So here we feed in the vertex position here, we put these into there, and then we undo the transform, and then we store this on the point domain. That's just the local vertex positions, and I can showcase this by using a set position node, and then putting in that named attribute. So vertex local position, if we look at this, we should see that all of the faces are now localized to 0, 0. These two vertices are aligned perfectly. That's very important. That's where the face corners are. And then everything else could be a little bit inaccurate. That's just because faces, if they're not triangles, are, well, even if they are triangles, are a little different every single time. And that's also why in the store transforms node, we go and do the tangent of the face corners first instead of the normal, because normals can be iffy if they're not on triangles. So there we go. Let's go and delete that and put this back. So next, what we need to do, since we have all that local data done, is that we just store a gradient, which in this case we can use the loop ID because that goes from, let's see if I can get the viewer node going right now. Let's see, attribute text. There we go. Here we can see that here, it's the loop ID is at 0, then it goes to 1, 2, 3, 4, and so on as you go up the mesh. That's what we want. That's how we determine this next part, which is how to stack the face transforms. Now this part is complex, so please bear with me. Alright, let's take a look inside of this node. And what this does is we just stack up the transforms that we have for the faces. So first of all, we have a repeat zone that goes through every single part in the loop ID. So every single loop that goes around, one value gets added every single time. That's what this node does. So it goes through and it says, hey, if this is equal to loop ID 1, 2, 3, so on. And then we can store the max iterations is just the max of the loop ID using an attribute statistic node. Not too bad. And then here we go. We just stack the data. So what we do here is, for the rotations, this is the most important part. We get the parent rotation, and then we apply the local rotations, which we can edit, as we can see here. And also, by the way, here I'm just flattening them out only on the x-axis, so that the main rotational axis is flattened out and these go straight. So the face local rotations, we put that in. We rotate that by that. Again, Euler and local, that's very important. Then we store it on the face domain. And then afterwards, the face scale, I'm not stacking those because just for simplicity's sake, we can affect those with the gradient and they will work just fine. I just don't stack them because it wasn't really necessary for this effect that I was going for. So next, what we do is that we do the new parent face transform using the parent data. For right here, we take the face local position, we apply the face parent location, rotation, and scale. We do the transform, we don't undo it, which again, just to show you this node group, it's not too bad. So there we have that, and then we store the new face position. And again, this is on the face domain, so the faces in theory are moved, but not the vertices. That is what we are going to do next. So this one is fairly straightforward. We get the local vertex position, and then we apply the new face position, face rotation, and face scale, using again that node, and then we set the position. So this is fairly efficient, and one of my more resource-intensive showcases, which this one is a human mesh. So when this mesh opens up, we can see that it happens almost pretty much in real time at 30 frames per second. Which a previous iteration of this effect that I made was 90 milliseconds, and the one before that was 120 milliseconds. But this, it runs at 30 milliseconds, which is very nice. So all of this is mainly to optimize for all the calculations. The repeat zone is the heaviest part of this. So doing everything on the face domain saves processing time because it has to do it for every face, which there are less faces than vertices or face corners. And then afterwards, we apply the vertex positions like that, so it is as fast as possible. But yeah, that is the effect and how it was made. I hope that explanation was fairly straightforward enough, understandable enough, even if you're not super into the math and indices. I know it was a lot. But if it was a good explanation, please let me know. And if you have any questions about it, please let me know. I have quite a few examples here. I want to try it out on more setups. But for the time being, this is where that effect is, how it was set up. And Intagma made a version of this effect in Houdini quite a while ago, which I referenced in order to make this one, so thank you to Intagma. Thank you all for watching, and I will see you next time. Have a good one.